A selection sort is an algorithm that can be used to sort anything. Say for example these cards here. To run a selection sort, what we first do is we consider the entire list as unsorted. So even though parts of it may be sorted, so the 1 and the 5 here in the right order, the 2 and the 7 are in the correct order, and by that I mean that the 2 is smaller than the 7 and the 1 is smaller than the 5. The computer is not aware or the algorithm does not consider those to be in any particular order. So for a selection sort, the entire list is unsorted. What we do is we look at the first element in the list, and this is considered to be the current smallest. If we were looking to sort it from largest to smallest, then that would be considered the current largest. In my case, I'm going to sort it from the smallest to the largest, and I'm going to use this marker to represent the largest element that I've found. So at the moment I've looked at the 3, so this is the one that I'm looking at, and the 3 is currently the largest element that I've found. So I move this marker to the next element in the list, and it's a 2. I compare the 2 and the 3 and see that the 3 is larger than the 2. So the larger marker remains there. Then I move this to the 7. I see that the 7 is larger than the 3, so I now mark that as my new largest. I move it to the 6, and the 6 is not larger than the 7, so this stays as the largest. I move it to the 1, or the next element along, and see that the 1 is not larger than the 7, so I don't move my largest marker. And I move it to the 5, and I compare the 5 and the 7 and see that the 7 is still the largest, so that's my largest number, because I've now reached the end of the list. What I do then is swap these two here. Depending on how the algorithm is written, it may not actually swap those two elements around. The algorithm doesn't necessitate that I swap. I could just shift things down. In this case, I'm going to swap them around. Then what we do is we mark this as sorted. That is now the largest element. I don't need to check that anymore. I know that that is the largest element because I've compared it against all others. Then we go back to the start of the list and mark that as the largest element that I've now seen. I move it along one and check, is the 2 greater than the 3? No, it's not. Is the 5 greater than the 3? Yes, it is. That's now the largest one that I've seen. Is the 6 greater than the 5? Yes, it is. The 6 is now the largest one that I've seen. Is the 1 greater than the 6? No, it's not. So what I do here is I swap the largest number with the end of the list, mark that portion of the list as sorted. I don't need to check anything to my left there, your right. I go back to the start of the list, mark the 3 as the largest one that I've seen. You may have noticed by now that it's a bit repetitive. By the time I get through to here, I will have found the largest item in the list. However, the algorithm doesn't take into consideration what is in the rest of the list. It doesn't know that this is actually not bigger than that until it checks it. So it still has to check it. So let's go through the third pass now. We look at that, it's the largest one we've seen so far. We compare the 2 and the 3, it's not the largest. We compare the 5 and the 3, the 5 is the largest. We compare the 1 and the 5 is still the largest. We swap those. Then we go and mark that part of the list as sorted. We go back to the start. The 3 is the largest. 2 is not greater than 3. 1 is not greater than 3. The 3 is the largest element that I've seen. We go back to the start and this part is sorted. We compare. Now actually, this is a good example. The list is now sorted. All these cards are in the right order, but the algorithm doesn't know that. It doesn't take that into consideration. In fact, no sorting algorithm will ever check to see if the list is sorted. By the definition of the algorithm, when it's complete, it will be sorted. It doesn't need to check. As long as the algorithm has been performed correctly, the outcome will be that the list is sorted. In this case, the 1 is the largest number that I've seen. I move it to here. The 2 is the largest number I've seen. The 2 doesn't actually need to swap, but it does in some ways perform a swap with itself. Then we mark that part of the list as sorted. There's only one element left. I still need to check it. It's the largest one that I've seen. There's nothing else to compare it against. I place it there. The entire list is sorted. And that is a selection sort. There is many problems with that. It does require you to make comparisons that are not necessary. So the way to determine how many comparisons it makes is it is quite a simple algorithm. It's quite a simple equation or formula. It's n, where n is the number of items in the list. So in this case there is 1, 2, 3, 4, 5, 6 times n minus 1. So 6 times 5 all over 2. In this case 5 times 6 is 30, divided by 2 is 15 comparisons. That is the maximum number it should take a selection sort to sort this out, provided that the instructions are given and followed correctly. And other sort algorithms will do that in a lot less, which you can look at in some of my other videos.